guys, this is Professor Janacek. I want to talk about the vector operation dot product and how it relates to projections. First, let's talk about the notation. Here we have the notation for projection of u onto v. Notice v is subscripted, but notice how I said it. Again, it's the projection of u onto v. The notation for the scalar component of u in the direction of v is here. This is the scalar component of u in the direction of v. Again, notice that we will we always have that v as the subscript. All right. So now there are a couple of things we can do with this just to kind of rewrite some stuff. Let's talk about this projection of u in the, onto v. Notice that the first part of that definition looks exactly like the scalar component of u in the direction of v, which means we can rewrite this as the scalar component times vector v over the magnitude of vector v. All right, so that's one thing we can do. There's another thing we can do. I'm going to use this little definition in place of that. So I know that the projection of u in the direction of v is the scalar component. So that means I can write this as u dot v over the magnitude of u times vector v over the magnitude of vector v. But notice this. If I take the magnitude of v times the magnitude of v, of course that's the magnitude of v squared, and if you look at how this all works out, it turns out that is the same as v dot v. Notice those are both scalar values, and if you look at how you find the dot product and how you find the magnitude and then square it, those are related, and that's the connection right there. So, turns out we can write this as u dot v over, now those denominators I've got magnitude of v times the magnitude of v, which we just decided is v dot v. And again, those are both dot products, so that's all a scalar value. And all that's left out here in the back is just vector v. So there's another way of writing the projection. So let's take a look at an example. We're going to let u be the vector 10, 5, v be the vector 2, 6. Now you could go through finding all of the dot products and stuff, but I'm just going to write those down quickly. If this is the case, then we know that u dot v is 50 and v dot v is 40. The magnitude of u is 5 square root of 5, and the magnitude of v is 2 square root of 10. So if you don't agree with those, or if you're uncertain of how to find those, take a moment, review how to find the dot product and how to find the magnitude, and pause the video and see if that's what you come up with. Okay? All right, so continuing on, let's go ahead and take a look at finding the scalar component of u in the direction of v. All right, so according to our definition, there's a couple ways I could look at this. I'm going to go ahead and take a look at not using the angle, because I don't have the angle, but it's u dot v over the magnitude of v. Well, we have that. That's 50 over 2 square root of 10, which we can simplify that, can reduce to 25 over the square root of 10. But also don't forget we can rationalize the denominator, which is always nice. If we rationalize the denominator, we get 25 square root of 10 over 10, which reduces yet again to 5 square root of 10 over 2. Well, there we go. It's all arithmetic, right? The real challenge here is doing the arithmetic. The dot product, not so bad. So now let's take a look at the projection of u onto v. Again, there's a couple ways of looking at it. I'm going to go ahead and use that last definition that we came up with. It's u dot v over v dot v times vector v. So let's see, that gives us u dot v is 50, v dot v is 40, and then vector v is the vector 2, 6. So if we reduce this, 50 over 40 reduces to 5/4 times vector 2, 6. Remember, you can multiply a scalar times a vector simply by multiplying each component of the vector times the scalar. Reduce each of these, and we end up with the vector 5/2, 15/2. And there you go. Enjoy.